This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you the next update for my spectrometer project. So in the previous video I have already showed you this little box. This is the PCB that I designed and built, which contains the linear CCD, and then this is basically the box, and this connector here is the SMA connector where this cable goes in. So I bought this optical cable which goes straight into this terminal, and then I can screw it on, as you can see. And once that is fixed, then the other side is, of course, can be connected to something else. So then we can look at the insides of this box. This is a 3D printed cover that I designed and printed myself. As you can see, it's 3D printed and it's relatively nice. And then these are the optical elements inside the box. I bought this from eBay, as is. And then the light comes in here, and then it falls on a collimating mirror, and then it's reflected on a diffraction grating, and then it's focused by that focusing mirror onto this CCD. And this is a TCD1304 CCD. And it's sitting on my custom designed PCB, as you can see. And it fits the box also perfectly. So when I put the lid back on the box, you can see that there are no sticking out parts. So this is the PCB which allows me to drive the TCD1304 CCD. And if you want to get your own CCD driver PCB, please visit the website of the sponsor of this video, PCBWay. They can provide you with all the necessary services to build this PCB. And I shared this design on my project page on PCBWay's website. So if you go to my project page, you can get this PCB, and then PCBWay will manufacture it for you. So visit PCBWay's website and check their services for your next project. So this is the setup that I use for demonstrating the capabilities of the spectrometer. And you can see that I have inserted a small blue LED in the SMA connector. So that's how I got the spectrum in the past. But now I have this FC connector, which goes on the other side of the optical cable. As you can see, it has that small notch that goes into the groove of that connector, and then I can just screw it on the thread, and I can attach this terminal to any kind of enclosures. So now basically we have the path of the light from that FC connector into the spectrometer box. And then I also have another toy, which is an electronic driver for high pressure sodium lamps. So this will be a nice tool to use. And then the output of this driver is connected to a normal E27 socket. So then this will be used to connect it to any kind of E27 bulbs or light sources. And then I have this box, which is a very nice box, and I will use this as an enclosure for the light source. So you can see that it's fully shiny inside, and it has this nice cap. So first of all, let's measure the dimensions of this box, because that will determine the dimensions of the bulb or light source that I can put in this box. And as you could see, it's roughly 10.5 centimeters in diameter and roughly 28 centimeters in depth. So that is basically what I can use for maximum size of bulb. And then the basic idea is to take the FC connector and then put it at the bottom of the box. So then the light will exit through a hole, and it will end up in the fiber optics. And then, as you can see, I can remove that cylindrical part from the socket, and then the plan is to put the socket on the lid like this. And then by screwing the two parts together again, I can clamp the socket to the lid. So I can remove the lid together with the socket all the time. So this is the hole. It's more or less centered. I removed all the sharp edges and burrs. So then let's insert the socket so you can see what was my idea when I was trying to explain that the socket is inserted in the lid. And then the threaded part is exposed on the other side, which is the inside of the box. So then I can take this other part of the socket and just simply screw it on the threaded part. And now we have an E27 socket which is sitting in the lid, and then I can put this on the top of the box. So we have an enclosure. And then here is the wall box with one FC connector on the side, so it allows the light to exit radially. And then we have the other FC connector at the bottom. And the reason why I did this is because different light sources emit the lights in different directions. So I can capture the spectrum of omnidirectional light sources as well as light sources such as spotlights. And the first light source is this high pressure sodium lamp. This was the reason why I needed to buy that driver circuit, which is in the background, that box with the Philips text on it, because this kind of light source cannot be directly driven by the mains voltage. It needs a driver circuit which provides the power to it in a proper way. So let's look at this light source first. So I will slowly power this up and then we will see how it develops its brightness and how it will look like. So you could see that it took some time to get up in brightness, but now we can look at the output of the fiber optics and we can see if we see any kind of light. And actually you can see that the end of this fiber optics is slightly orange, but maybe it would be more helpful to turn off the lights. So now we can see the light with a bit better contrast. And if I point it towards my gloves, we can see the light. But it would look even better if I would point this at a bright surface. So this is a white box and you can see that something is coming out from this fiber optics. And in the meantime, don't forget that this is a high power light source. So it generates a lot of heat, and this becomes especially dangerous when it is in an enclosure, because then of course most of the heat cannot be dissipated that easily. You can see that the temperature can go as much as 73 degrees Celsius. So I just shut this thing down, remove the lamp and let it cool down before I damage it in some way. And now the next task is to check different light sources, for example this one with my spectrometer. So we will go to my computer and I will guide you through some things which can be interesting for this project. So now we are at my computer and we are looking at the software that I developed to communicate with the microcontroller and receive and process the data from the spectrometer, or more precisely from the CCD that I'm using in the spectrometer. And then what this software does is that after a calibration it can show the spectrum with colors and wavelengths and everything. And I already showed this software in the previous video, but I did a little change now. So in the previous video there were only 2 points for the calibration, but now I'm using 4 points. So basically I can have a set of 4 wavelengths pixel peak pairs, and then using these 4 points I can do a linear regression, and then based on that linear regression I can calculate the intensities back to wavelengths, or not the intensities, but the position of the intensities, because each peak which will be generated by the light source will be located above a certain pixel, and then this pixel number can be let's say calibrated, and then it can be converted into a wavelength. So then instead of seeing that we have a peak about the 500th pixel, I will see that we have a peak at 624 nanometers or something like that. And then the first thing what we have to do is that we have to grab a light source, which will be a high pressure sodium lamp, because it has several well distinguishable peaks. And then we have to grab its data sheet, where they typically publish the spectrum of this light source. And then we have to fetch some of the peaks. So what I'm going to do there is I will show you how to do this. So there is this very smart website which is called Web Plot Digitizer. You can find this website through my blog article, so check the link in the description. And what you can do here is that you can load any kind of image that has a chart on it, and then you can calibrate the chart with a few known points, more precisely 4 known points, 2 points on the x-axis and 2 points on the y-axis, and then wherever you click on the chart you will get the xy coordinates. When I did my PhD I used this a lot, because I had to dig through a lot of old articles, and they obviously had to be somehow reverse engineered, and how I got the data from those old articles it was basically this way. So I digitized those pictures, and then I could like extract the data, and I show you how it's done. So here I just load an image from my computer, and then here I select the 2D XY plot, and then here we can see the instructions. So first I have to select 2 points on the x-axis and then 2 points on the y-axis, and we can see the order. So from low values to high values we go. So then I proceed. So here I select 480, and then I select 680, and this is also good range, because this basically covers almost the whole visible light spectrum. And then comes the y-axis. So let's say here we choose 0.2, but the y-axis won't be interesting for us, because I'm just using intensity, but it's in arbitrary units, so we don't have any units here. And then I select 1 here. So this is done. And then I know that the x-axis belongs to 480 and 680, and the y-axis is 0.2 and 1, and I just say OK. So now I have to select a few peaks. So I have 4 calibration points, so I will choose 4 points. But I want to choose points across the whole range, because I want to like scatter my calibration points properly across the range. So let's choose this large peak here. And then I choose this large peak around the yellow color, and then these 2 guys here, just for fun, just to see where they are, and then this red peak as well. And then I can view the data, and then basically I can note these down, because the only thing I want to know now is that I have these certain peaks here in the background, and I want to know their wavelengths. That's all. So I just copy these out somewhere. So this is done now, so we can return to my software. So here's the software, and I have already connected everything, so I just have to connect to the USB. So that's done here. And now we don't use the calibration yet. I have some parameters from earlier trials, because I made a function to this software that whenever I enter these parameters, they are saved in a text file, and whenever I restart the program, I just load those previous values from the text file, so I don't have to enter them all the time. But now I just choose some relatively low integration time, or relatively fast integration time, if we say it like that. And then I just start. So we have this spectrum, which is now the uncalibrated spectrum. And what we see on the x-axis is the number of pixels. So on the left, very left side, that's the 0th or first pixel. And then towards the right end, that's the very last pixel on the linear CCD. And then the intensity is actually just the digital bit number from the AD converter. So it ends at 4095 because we have a 12-bit ADC in this microcontroller. So now what I have to do is that I have to start the light source. And before starting the light source, I have to notice something. I showed you when I assembled this thing and I made the box that I have a optical fiber or fiber optics. But it doesn't work properly. So I discovered that if I don't insert the fiber optics in the spectrometer fully, I get different parts of the spectrum visible, but I can never get the whole spectrum visible while using this optical fiber. And I don't know what's the reason, but I have one guess, and that is that the core diameter of this fiber optics is only 100 micrometer, and that might not be sufficient. I looked at other fibers at 200 and 600 micrometers, but they are rather expensive, so I have to save up for it. So now I just directly plugged in the SMA connector into the FC connector on the pasta box that you saw I drilled and assembled. So then let me start this high pressure sodium light source, and let's see how the peaks develop. And in the meantime, I fill in the peak numbers, at least their wavelengths, and then once the peaks start to show up, I will also be able to identify where the peaks are located in terms of pixels. So now you can see that we start to see the peaks. As the lamp is getting more and more warm, then the pixels also have larger and larger intensities on the CCD, because of course the emission of the lamp also increases. But now we have like stable positions of those peaks, and that's nice. But before doing the calibration, I want to show you something. So now we have this spectrum, and you can see how it is aligned. But if we look at the spectrum that we are recording right now, we can see that this is basically the mirror image. So you can see that this high peak is actually this high peak, and then comes the two peaks. So we have to be careful when we do the identification. But nevertheless, I know that this peak here is the lowest wavelengths. So this becomes 2776.81. And then the next, which we selected, is this high, which is this high here. And then we have these two pixels here. And I noted down the second one, so 593. So this guy here, the more red, which is then this one here. And then finally, we have this peak on the shoulder, which is this guy here. There. So I apply these, and that will save everything. And now I use the calibration parameters. And now it's flipped. So I save this picture and then recall this picture in Paint. So now this is probably not the nicest picture, as you can see, but if you go to my website you will see the full resolution picture where I made the comparison nicer. But you can see that if we neglect this baseline, which I can actually subtract if I write the software a bit more carefully, other than that we have almost a full identical set of peaks here. So actually down to, let's say, 450 we have the peaks, and then as we go to or towards higher wavelengths we have all the peaks. So this guy is just here. I try to align everything that they are under each other, and everything is at their corresponding position. Even this small shoulder should be this small shoulder here, and then towards the higher wavelengths we have the same kind of shape. So that's really nice. And what would be interesting now is that I have a few lasers here, and we could look at their wavelengths. If after this calibration I can get the same wavelengths that is stated by the laser manufacturers. So let's head back to my software. So the software is still running, but now I turned off the light source, so there is no light. What I'm going to do now is that I'm going to shine the laser through the port and see if we get a peak. And I don't tell you what color I shine, because you will probably see it immediately. And there we go. And I will try to measure the wavelengths of it, of course, if I manage to generate a nice peak. So this says 678, but according to the description of the laser, this should be 650 plus minus 10. So it's a bit off. And then this will be another laser. Which is 528. And according to the laser's datasheet, it should be 532 plus minus 10. So this is within the plus minus error. So all we can see is that the spectrometer has a bit issues towards the edges of the range, but otherwise it works quite okay, I would say. And then we can even investigate other light sources. So since now we have a reasonable calibration, let's do that. So we can see that the peaks are not growing that much, because this light source is reaching its, let's say, operating temperature and conditions relatively fast. So actually the brightness of this is much lower. Therefore I have to change the integration time to longer times. So let's do that. And now we have nicer peaks, as you can see. So this is a fluorescent tube. So let's see if I can find some resources on the internet. So this is the image that I found on the internet when I was just simply searching fluorescent light spectrum. And obviously somewhere there should be a set of numbers which identify the peaks. So let's look at that. And once again, this will be listed more carefully on my website, so check my website as well. So if I close the full screen image, then I have this page, and if I scroll down, I can see the wavelengths of each peaks. So let's check a few peaks. So for example, we have 4, 5 and 12. They are really high and easy to identify. So let's check what is their wavelengths. So 4 is here, 542 and 546, and 12 is 611. So I grab my software, and then we can see the same peaks. So this should be 4, which is like, yeah, off by a little bit. I can actually cheat a bit and do this. So this is supposed to be 542, but I measure 538, so off by 4 nanometers. And then the next one should be 46, but that is 41, so still we have the 5 nanometer shift. And then the 12 is here. I mean, it's here. That is around 613, and here it's 611.6, so 612. So that is like plus minus 1 nanometer. It's fine. So let's check a few more peaks. We see that towards 400 we have like 2 peaks. So let's see if we can find it on the chart. So one is here, which is at 491, and that should be peak number 3. So 491.7 versus 487.7, so 3 nanometers. And then we have this peak here, which was peak number 2, and that should be peak number 2, 436. But I measure 454, so it's a bit higher. Even if I go here, it's much higher. So this kind of confirms that I was suspecting in the earlier video as well, that towards the edges there is some issue with the optics probably. So for example, the projection of the spectrum is not entirely flat. So then it is projected or focused in front of the linear CCD or behind the linear CCD. Therefore, it's like focused on a kind of a curved surface. And therefore, towards the edges, I don't have that nice precision. Because if we go back, let's say, here we have a bunch of peaks. And if I check one large peak, which I don't really know which could it be, then I probably get much better, let's say, agreement. Let's say 11 is probably this one here, which is at 599.7, and here I have 598, so that's like spot on. So towards the center, I have very good spectrum, but if I go towards the edge, the more I go towards the edge, the less accuracy I get. But probably this could be also a bit fixed if I calibrate at a larger scale. So for example, starting at a very low wavelengths and ending at a very high wavelengths. So that could help. But yeah, we can see that this works. So let's try to find another light source. So again, the spectrometer is still running, but the light source is turned off. So I turn on the light source. And this one is a boring spectrum. And why? You can see that it has almost a full coverage throughout the visible spectrum. And the reason is because this is an LED light source with a quite white light. So therefore we cannot really have any, let's say, distinguished peaks. But nevertheless it looks nice. But yeah, we don't really have to deal with this because it's rather boring. So I don't have anything to explain about these peaks or bumps. So let's proceed further. So the next light source is a bit tricky, so let's see if we have enough brightness first. And there is basically nothing, so let's increase the integration time. And there is still nothing. So now I'm adjusting the position of the light a little bit. And as you can see, we get similar bumps as we could see previously for the LED light. And the reason for that is because this is a tungsten filament light source or incandescent light source. So it has again a very smooth spectrum, as you can see. So that's that. So now let's check a few LEDs and let's see how they look like. So I will just plug in the LEDs directly in the port, the SMA terminal of the spectrometer, and then we will see how the spectrum looks like. So this is the first, and I let you to think for a few seconds what this LED could be. But a few hints is that this is also quite well distributed across the whole range of colors or wavelengths. So this is a white LED. So now let's go to the new LED, which is a different color. And well, this is not difficult because you see it on the chart. This is a so-called amber or orange, yellow, however you want to call it, color. And again, we can even change the wavelengths. Actually, you can destroy a green LED and make it into yellow if you give too much current to it. And this happens with this LED as well. So let's destroy it because I have 100 other. So now we have more like a red LED. And it's irrecoverable, so, or irreversible. So don't do this too often, especially if you want to measure their wavelengths later on or use it, because now this LED is basically destroyed, to some extent at least. So let's check the new one. Again, this will be easy to guess based on the peak's color and the location. So this is a blue LED, of course. And again, if I give it too much current, then it goes towards this turquoise color here. So you can see that the peak is shifting a bit. So now I'm destroying it, basically. You can see I'm not changing anything, but I'm giving it too much current, and now we have some green and other colors in it. So now I decrease the current, and you can see how it behaves. So then the next one, which I show you, might not represent the original color of the LED, because I have already destroyed this to some extent. Yeah, it doesn't even work. This is supposed to be a green LED, but I cannot demonstrate it because it doesn't work. At least not at this exposure time, so I will change it in a moment. But I have brighter LEDs, and then you can see that I even have a red LED. And it has quite broad spectrum around the red colors, so it contains all the red shades, let's say. So coming back to the green, I inserted the LED in the hole, so I stopped the acquisition, and let's say increase the integration time significantly, and there is our peak. So that's a green LED's spectrum, and now it turns into yellow because I increased the current too much. But yeah, you can kind of see the peak. Now it's visible. So this is a green LED with a semi-destroyed circuitry. So its spectrum is probably not the most accurate one, but it's there and it shows something green. So basically this is what I wanted to show you, that I built this new box, which is my, let's say, light source box. But as I discovered, the fiber optics was not perfect, so I could not get the light out from the box using the optics. But nevertheless, I could get the light out, and you could see that we could measure the spectrum of a high pressure sodium lamp quite accurately. And then we can also use the peaks from that spectrum and use it to calibrate our spectrometer, and I showed you how to do that. So that's really nice. So then in the next iteration of this project, I will try to buy a better fiber optics cable, but probably in a few months, because I need to save up for that. But if you want to speed up the process, then you can consider supporting me on Patreon, because that helps me to buy these gadgets and stuff, so I can make more videos. So please consider supporting me there. You can find the link in the description. Also go to my website, because I uploaded a lot of extra information there, more pictures and better pictures as well. And of course, if you want to build your own spectrometer and want to use my PCB design, don't forget to visit my project page on PCBWay's website, because I uploaded the PCB there, and then you can use PCBWay's services and get the PCB and build it, or even ask PCBWay to build it for you. So please check all the links carefully in the description, and then see what they contain, and then enjoy this project if you try to rebuild it. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.